I want to say that anything I know about insurance is because of my collaboration with Faye. And anything I get wrong should not be blamed on her. I'm a statistician, and I've worked in, we heard a lot about transparency and explanations for pricing models in the panel. I've spent a significant part of my professional career on what does interpretability in machine learning look like, and what are the statistical processes through. The spoiler alert, I'm a statistician. I complain a lot, but there's actually a lot of potential pitfalls in how you're doing things. And I thought that mostly what I would do is work through this. Some of that will be with insurance, some of that I've just taken some toy data sets to illustrate points. A lot of this work is with Faye and our student Shi Xin. It's been wonderful. Along with this also owes a lot to many other students, 4 of whose last name was Joe. But I do work with people whose last name is not Joe as well, and they're all wonderful. But let me get started on. So the overview here is, I thought what I could most helpfully do in this context is to try and produce an overview of interpretability methods in machine learning. That's ambitious for a half-hour talk. Bear with me. Do interrupt me, too, if there's anything you don't mean. And associated statistical challenges. And I'm coming here from saying, look, if you look at what, not just insurance, I mean, statistics or anything else in general has been based on, and the sort of models that are used, up until recently, they have been fairly low-dimensional, parametric, and you could discuss what was happening in terms of the components of those models. And modern machine learning techniques that I will date from about 1990 have really blown that up, particularly their use of them. And that is exacerbated by AI. So you suddenly can't inspect the internal components of these models particularly well, and you're relying on some way of querying their outputs. And then we'll ask about what does that mean for interpretability. There's been a whole lot of these tools that were developed from starting about 25 years ago. And that's about when I started starting to yell about them. And what I really do want to illustrate is that for a lot of these tools, they were developed by people like me, for people like me, who wanted to use them to sort of sanity check the sorts of models they were getting without having a formalized system. Once you want to start doing something like regulate the tools that you're using, the fact that you are making formalized statements about this makes some of their deficiencies much more important, and you need to think carefully about it. So I'm going to give you a little taxonomy of interpretation, some of the specific challenges, and I'm going to end up without spending enough time on this, but I want to talk a little bit about, well, hang on, there's multiple levels of uncertainty. And what are you trying to quantify or control? Because that's one of the current topics that I see people confusing a lot when they start talking about uncertainty quantification. So a little taxonomy, and I maybe should have started with the next slide at first. I'm going to say, okay, I've got an insurance price. It's developed from whichever machine learning system you particularly like. And we had John Johansson saying, well, look, people want explanations. In fact, there is a famous paper that arguably kicked off the recent, decades, literature on explainable machine learning that's titled "The Doctor Just Won't Accept That." And the abstract is, I work with radiologists. You can't just tell them your patient has cancer because the machine learning system says so. They want to know why. So this is a more general problem, and it's been around about a decade. So what sort of strategies might you have if I'm saying, okay, I've got some model that's giving me an insurance price? Well, you can ask about a few distinctions I want to make here. You can ask about global patterns, which might apply to things like fairness metrics. Are we overall discriminating against women, older people, Black Americans, etc.? Or you can ask about what drove local patterns, what drove this particular decision. Why is my insurance rate going up? The classic version in the interpretability literature isn't insurance, it's why didn't I get this loan? But still very simple. And then you can have various strategies for trying to provide those insight into either of these questions, you can have an interpretable model, and by an interpretable model, I usually in the literature seems to have come down to something like a human could actually get from the inputs to the output as being this is how I can make this model accessible. I could have some form of a summary. What are the important features that mattered, either to this explanation or overall, or it could be an example. These are people who did get the loan, or these are people whose insurance rates didn't go up. So those answer different sorts of questions, and they have very different strategies. If I think about what happens in insurance, right, if I'm looking at regulation, that's often of some sort of global factor, right? I'm going to be interested in overall levels of discrimination, relative importance of factors overall for the price. If I'm talking to the public, I tend to care about giving somebody an individual local explanation of what mattered to your insurance policy. And that can be a justification. It can also be advice. It can also be, here's what you would need to do to have, not have your claim denied, to get the loan, to reduce your price. They provide very different information. Things can look very different depending on the lens you look at. And a lot of what I'm going to say is that, hey, a lot of the time these have fairly poor statistical properties, and you need to be very careful about how you start using these tools, or how you start designing them. So let's talk about, some of the tools that have been used. One of the first things that people ask is about what's important. And variable importance is one of the oldest parts of these measures, or the measures that have been developed within the machine learning literature. So if I have an insurance price that's a function of some set of inputs, these are your credit score apparently. I wasn't as aware of that as I should have been either, as well as, if it's auto insurance, like driving history and what make of car I have, et cetera, et cetera. And I could have asked, how important is X1? How important is my credit score, right? And if you look at things like the California Prop 33 regulation, it says, well, the following 4 factors have to be the most important thing. And in fact, they have to be most important in this order. And so, okay, well, what does that mean? So in the context of machine learning, people have talked about importance by, well, some machine learning methods have internal structures that you could base importance around. You look at random forest or tree-based methods, there are tools that you can use there. You probably don't want to insist that somebody uses a random forest. So there are also a bunch of model agnostic tools, and the machine learning community loves developing model agnostic tools. It doesn't matter how you got this, we've just got an input-output black box relationship. And you could ask about, well, what happens if I remove X1? What happens if I don't give you that information? Or you could ask about what happens if I replace X1. And I'm going to walk through just a little bit of work here to say, well, let's actually talk about mechanics, because it makes things a little more complicated than you might think. So one approach, I should have put a reference here. This is by Larry Wasserman, is leave one covariate out. It's the obvious thing you think of if you're a statistician. You say, cool, I'm going to assume that I've got a prediction problem. So, rather than price, or by proxy, I am measuring the output payout from claims. I want to predict what that looks like. I'll write, I'll get my machine learning system, I'll train my F, and then I'll ask about, well, what happens if I didn't give Fx1? So I'll take that column out of my data set, and I'll train another model to say, how well can you do? That seems very sensible from a statistical point of view. And I'll measure, usually I'll have some measure of performance that's given by a loss, so an error rate, and I want to make that small, so I'll say, how much worse did I do at prediction? This looks a lot like change of sums of squares in linear regression. If you took linear regression a long time ago, it's just, hey, my model's more complicated. So problem. first of all, my pricing model isn't always a prediction. Now you could say, okay, maybe it comes from some sort of prediction. I could possibly work something through, but it's not always directly. Originally, like, we used this as a test for, does X1 matter at all? Now, the statistical properties of that test when I'm applying a machine learning model are unclear. In fact, my student Lucas Mensch had some beautiful examples where just giving a random forest additional noise makes it do better. Actually, no, seriously. In fact, this is semi-shocking, but it does. More importantly, from the point of view of trying to design something for regulation, I'm interested in F. I'm not interested in this F1 tilde that I trained just to say how much better is F than F1 tilde. And in fact, that gives me a lot of room to start futzing around in terms of, well, how well did I train? Maybe I care a lot more about training my F1 tilde when there's a variable I don't want to have, make look so important in there. So it adds additional things I need to start specifying about how much work I need to do within doing this. And you're really asking about not the model that's in front of you. So an alternative is to say, well, instead of dropping x1, I can fix my f. I'm just going to change the values for x1 that I put in. I'm going to give you a different credit score. So I'm going to replace x1 with some x1 star and ask about how much worse that makes my prediction. And that's fairly, that sounds fairly nice. It only uses f. It says, okay, what happens if I change your x1? And then the question is, well, how do I choose that x1 star? And there's two ways that this is being done. Permutation importance, this goes back to 2001 with the original random forest paper, says, okay, cool, I'll tell you what you do. I'm just going to look down my set of x1s, and I'm just going to pick one at random. You'll get somebody else's credit score, chosen completely at random, and we'll say, okay, what would your, what would your price look like, or how much more would we lose if we just randomly shuffled my credit score column? And I'll talk about that a little bit later, because it turns out that that can have quite poor statistical properties. The alternative, and it stems from basically saying, hey, I am middle-aged, white guy, driving a pretty nice car, but with good driving habits, it's quite unlikely that I'm going to have a credit score that's completely in the tank. And so pairing me with that credit score is fairly unrealistic. You might say, well, maybe I should just say, well, I'm going to generate a new credit score for people like you, right? I might have a range of potential credit scores, and we'll pick from somebody who's similar to you. And the problem with that is I've now created yet another model that I now have to talk about, right? What does people like me look like? And this is, again, an opportunity both to sort of futz your results a little bit, or alternatively, a need for much further specification about exactly how do you go about doing this. This is, in fact, the variable importance that comes out of random forests. It even gives you a little error bar on it, which is nice. We'll talk about how I should worry about what that error bar might mean. And, in this case, I've taken an ancient data set. This is a 50-year-old data set on housing prices in Boston. It's one of the classic ones. I've used it because there's a plot that I really want to illustrate the next effect on in it. But you could then say, okay, my credit score matters or something matters. Here I'm looking at prices of houses and these are median prices in zip codes in Boston. And you could say, okay, well, X1 matters. In what way does it matter? And, well, okay, a few things you could try and do. You could produce what are called individual conditional expectation plots that just says, okay, I'm going to take one individual data point, I'm going to change the value of x1 across a bunch of different values, and I'm just going to trace out what that does. And that's each of these little faint lines on the right-hand side is an individual conditional expectation plot. And you could say, well, that's a lot. What should I do? Well, maybe I should average all of these to get you the red line. Because of the breadth in the ICE of variability in the ICE plots, the red line doesn't look like it's doing much. It does sort of dip down. This is the crime rate in that neighborhood, so it does dip down a little bit at the start, and then it's fairly flat. And this is, in fact, we got the red line first. Jerry Friedman did this also in 2001. 15 years later, Goldstein and co. managed to say, well, maybe we should disaggregate and get another paper out of it. It was kind of cute. But, okay, this seems like a sort of kind of reasonable summary of how, say, crime rate changes things. It's just the very start that matters. What I want to do is illustrate, here's why this is a challenge. And I've been yelling about this for literally 20 years. And people still do it. So I've plotted here the crime rate in this data set and distance to your major arterial highway, major employment centers. And the blue dots are the data that we have in the data set. The red dots are all the places that I have evaluated, in this case a random forest, when I've created those, both the partial dependence plot and the variable importance. And the point is that I'm mostly measuring whatever it is that my model has decided to do out here, where one, I don't know what the truth is, have no notion about what the truth is, it has no information, and two, I'm never going to see data that looks like this. I started yelling about this 20 years ago. When my student Lucas Mensch started doing some work on this, we noticed people using variable importance tools to screen genes to look at for cancer. We thought maybe we should actually check. It turns out, now, I'm going to call this, I should anecdotally, because we can give you a simulation where this happens, what this effect does, is it inflates the importance of all the features that are correlated with other ones. So it takes anything that's correlated and it kind of gives every one of those all the signal. So it can significantly distort what you want to look at. That's relative to a simulation where I know what it should be out here, of course. And that will come up in a minute. What does that do to us? So here's some work that I did with Faye using this. Rather than looking at variables, we looked at partial dependence plots because there had been some auditing procedures that had been proposed that says, well, you should look at partial dependence plots. So here's an insurance data set. I've got a driver's age, the age at which they got their driver license, and we've looked at claims payouts. We built a model, and we got the following partial dependence function for age. It's maybe not surprising, early young people are young and stupid and inexperienced, and then you start getting old and, you stop having the reflexes, etc. But what you'll notice is, you can't have somebody get their license, be younger than when they first got their license. So I've got all of this room here to do whatever I like with. And in particular, what we did was we just said, well, if you're worried about age discrimination, we can make this 0. All I can do is invent something to put in here that exactly cancels out this effect. Now, we don't need to have that kind of impossibility. We actually did a bunch of simulations where you could have even not that much correlation and sort of just get a little bit outside of the potential set of joint values that you have and be able to still sort of zero out the effects that you're interested in. We did some experiments with zeroing out more than one. Combining this with other explainability tools makes that harder. So there are certainly ways you could try and catch that we're playing some games here. But we could do this also without ever changing any of the prices that we would actually charge somebody. From a commercial point, it's actually free. Now, nobody's actually going to do this, I suspect. But in terms of this, it was an illustration of the sorts of effects about why you need to be careful about where you're defining these problems. Okay, I want to turn briefly to local approaches and to say, okay, what matters for this prediction? And again, there's a variety of things that you could do. You could ask about what happens when x1 is changed, right? Here's what happens if you up my credit score by 10 points. Well, why 10 points, right? I mean, that's sort of suddenly hey, what scaling do I need? And again, there are choices, and that changes the answers you get. I could take a derivative if I'm using a differentiable model. I could use some local approximation, and in fact, those are tools that I'll talk about on the next slide. I can use maybe, a change in prediction when I take out the information for x1. I average that out somehow, and that also yields the same sorts of challenges that we talked about before. A couple of other interesting ideas, counterfactual explanations. Kevin Werbach talked about this briefly. What do I need to do to get to a decision or to get to a prediction I'd be happier with, right? How do I get that loan? What does somebody who gets that loan look like? Well, that's potentially a justification, right? Here's how you are different from somebody who gets the loan, legally standing maybe. It does lead to questions about, there's lots of people who got that loan. Who do I show you? Close, what does close mean? It also has some potential interest if I'm actually making this a promise, right? Because potentially, right, if you go and increase your savings rate by X amount, we will give you the loan, right? Or if you go and increase your credit score by 10 points, your insurance premium will come down. That's distorted the data that I use to train on because I've now given people an incentive. And in fact, I'm not aware of great tools for accounting that as yet. Shapley values have been enormously important. My basic statement is enormously popular. My basic statement is please don't use them. I don't have the time to tell you about what Shapley values are, and that is my first problem with them. They're fairly complex. They have a justification that comes out of economic game theory that I think is pretty tenuous for our use cases. They definitely don't work for somebody in the public. They're actually fairly unstable too. So I did some work on ranking stability, and just the calculations you do can leave you with fairly strongly unstable ranks. In the interest of time, ALE plots are an interesting way to try and go from sort of fairly local to global problems without having extrapolation problems. They have a lot of tuning parameters. They're very interesting. I like them a lot. They have a lot of tuning parameters. Their approximation properties, if you start caring about these things, are not always obvious, but they're nice. And then, like, the last topic I want to talk about is surrogate models, because this is interesting from the point of view of uncertainty quantification, right? One of the things you could do is to say, I'm going to build some human intelligible model that's going to mimic the machine learning algorithm. Usually a human intelligible model means a decision tree. Decision trees were some of the very earliest machine learning algorithms out there. They go back to the late 1970s. They're not popular because they don't perform well. But they don't perform well because of the way they're trained and because you've got limited amounts of data. So if you see Cynthia Rudin's done a huge amount of work on saying, hey, actually, I can make systems that come up with a set of logical rules perform really pretty well if I have some specialized optimization tools out there. And it's Cynthia's done some incredibly impressive stuff. You could do something a little more careful, a little less careful. I could just say, well, if part of the problem is I don't have enough data, I can just generate data. So I'm going to say, okay, build your neural network, your random forest, whatever non-interpretable thing it is, create a huge data set so that you can now produce a tree that does perform well. Because I can make my tree give predictions that are as close to that random forest as as I like if I can keep generating data for it. And trees, again, it's a nice set of decision rules. So it's regarded as very interpretable because that's something that a human can produce. Here's an example of this. This is from 15 years ago. I was working with some people in psychiatry, working on diagnosing severe depression. Now, the standard depression diagnosis form is a questionnaire that runs to 88 questions. First indication you might be depressed is you don't finish. Right? It does, in fact, pose a fairly significant burden. They say, can we do a quick screen to say, look, we don't need these people. They're fine. We only need the psychiatrist to look at these. So I generated, I had about 800 observations. There were 88 questions. I generated about 1,200 new observations, built this tree. I don't remember what question V52 was. At the top of the tree, it was something like, how often have you felt good today, right? And, I basically gave it, that got me identical test set performance. That's great. Question was, what if I did that again? Same random forest. Didn't change the random forest. New 12,000 samples. Still V52 at the top. Second layer of the tree is already completely different. Okay, when does that matter? I don't think it mattered here. It was just screening. I didn't care about the questions. But if I was using this to tell somebody why you didn't get a loan, or it was meant to have some causal implication, things start getting dubious. And you need to be careful about it. We did some work on how many data points would you need to recover the same structure. Turns out like orders of magnitude more than you would think. This comes up in some of the local explanations. Line fits a linear model locally to data with a penalty, so it only gives you about 5 terms. That turns out to be super unstable. And especially the way they give it. You do this again, you get a different answer, right? This is not great. We sort of distill things into additive models. That's more stable. You have some nicer terms. If you look at fairness assessment, and Faye's going to talk about some of this for part of her talk, you have a surrogate measure, that model that sort of regresses price on like protected attributes or something else. And there, I've got a fixed set of protected attributes, but the uncertainty quantification has to be different. So we need some different attributes. Brief plug for another paper by Shi. We looked at BISFG, imputation of race. The errors in that introduce real biases in the answers that you get, and that was a really interesting eye-opener for us as well. I'm going to finish, and I know I'm sort of basically taken all of our time, but the last thing, I want to talk a little bit about this uncertainty, right? Because we have to ask about, what do I need to control or understand? Now, in the case of my decision tree, if it's sufficient for me to say, here's how my decisions are made, and I'm not using the random forest anymore, I'm using this decision tree, I don't care if it's random or not, that's fine. This is the human intelligibility is fine. But if you want to go on to say there's causal implications, or I'm doing that again, suddenly this becomes a problem. So what's uncertainty here? Well, there's the intrinsic stochasticity in the algorithms we use. That's true both in how I train my models and true in my true in my explanation system. I can sometimes control that. If I'm evaluating something like a fairness metric, I'm using a test set, I'm plugging in a known set of test values. That might be something I'm worried about. That's relatively easy, but non-standard to work out ways to work with. What about if I'm worried about the uncertainty in my model itself? I want to say, if I got a new test set, new data set, trained a new model, what would that look like? We've done some tools. Some of my students, Xiaohuang, Jeff Zhou, Alexander Hasamoda, actually specifically on fairness, has done some work on that. That's a lot harder to do. It's not always what you want. One of the things that I haven't seen people really discuss is, hey, which of these things matters? Which of these things matters for this problem? Why am I choosing this tool? And those are actually, I think, really important to get straight, particularly once I'm starting to talk about formalized requirements. Okay, I think I've got 2 minutes before the end of the talk. Faye started early, so she got me there just on time. I don't know if you want to moderate questions. I wouldn't take more than one because I want Faye to talk about some of her really fantastic work as well.
It's a great presentation. I thought like your algorithm I used like example decision tree, random forest that's intuitive and that's lower end of technology. Nowadays, people are using double machine learning to deal with the uncertainty you're talking about. Have you have extensions?
Well, double machine learning doesn't really deal with uncertainty. Most of these tools don't care about how you got where your where your model came from.
So the double machine learning, they have a first step using Neyman's orthogonal.
Yeah. You're talking double machine. Yes.
Yeah,
So yes, double machine learning, targeted learning is in fact the framework we use to assess variable importance and fairness. Yes, you can do those things. They talk about this property, right? What if my model was different? Like, what if I had new data, trained a new model? They're pretty hard. They're not always simple to work in. You often need auxiliary models, so that's challenging. But beyond developing the technology, there's the question of, is this the thing I wanted to work with? Is that the thing that's relevant? And the answer is sometimes. A lot of the times, no. If I'm a regulator, I probably care about this model that you're using, not about what some hypothetical alternative would be. But we need to actually be explicit about it. I had one other question, and then I'm going to introduce that.
One second. What are your thoughts on conformal predictions? Secondly, what is the data correlated? Is it spatially, temporally, and
So, excellent questions. Conformal prediction is maybe something I should take offline. I'm not sure that it's helpful for insurance in terms of setting out risk bounds for themselves. It's less relevant for, well, maybe it is relevant if I'm worried about the stability of about the solvency of an insurance company. Correlated data is a real problem because almost nothing in machine learning actually deals with it. We all assume IID data, and there's no data set that I've ever looked at that I believe that in. There are some tools that can help, but that's an area that is really still being developed. Okay, I am going to moderate my own talk and say, well, we're going to stop because I really want to hear from Faye as well.